This is Wastewater Treatment Certification Training, Chapter 5, Part 1, Physical and Biological Treatment Processes. In this first part of Chapter 5, we're going to go over primary clarifiers. We'll start secondary treatment, dealing with the fixed film systems, trickling filters, and RBCs. Primary clarifiers. The purpose of a primary clarifier is to create a relatively still area where solids that are heavier than water settle out as sludge. It also allows solids that are lighter than water to float to the surface, and the skimmer can skim these off. This will reduce the organic load to your secondary treatment system. Here's a circular clarifier. The influent comes in the bottom up through a central pipe going up to the top. That opening in that pipe is surrounded by a stilling well. What the stilling well does is it breaks the flow of the water coming up and into the clarifier so it doesn't mix up the solids that are settled at the bottom. Then the heavies settle out as sludge. The sludge will normally concentrate to about 4 to 8% solids in the primary clarifier. The clearer water will go up and over the weirs into the launder and out to your secondary system. There's a picture of a circular clarifier. It's the unit in the front of the picture. The two in the back you see there are what we'll be talking about later this chapter, a trickling filter. Rectangular clarifiers exist. Typically their sludge rake is on chains, and the sludge rake also serves as the skimmer to skim the scum off the top. You'll notice there is a wall, a baffle, where the water comes into the tank to break the flow so it doesn't scour the bottom. There's a picture of a rectangular clarifier and another one. The skimmer removes the floating materials, fats, oils, and grease, as I said, to reduce the loads on the biological treatment unit. Clarifier sludge. Sludge should be pumped often and in small quantities. You do this to prevent hydraulic and organic overloading of the digester. You do this to prevent septic floating sludge by keeping the blanket down. Sludge accumulating in the clarifier will be between 4 and 8% solids before transferred to a digester or to another way that you're going to dispose of it. Best practice is maintain less than 3 feet of sludge in your clarifier at all times. Some of the factors that affect settling in your clarifier: the concentration of your solids. The heavier and larger suspended solids will settle faster. The more particles you have in there usually equals faster settling. Temperature. Water is less dense at high temperature, thus more rapid settling occurs. As the temperature drops and the water gets denser, it will slow down the settling of these particles. Typical detention time in a primary clarifier: 50% of the solids will settle out in about 30 minutes, 60% in about 1 hour, and 70% after 2 hours. Clarifier design. Typical detention time in primary clarifiers range from 1 to 2 hours detention time, but can go up as high as 4 or 5 hours. You can use a settleometer to test your influent to check how long the solids take to settle and how long the solids can be in the clarifier without floating. Causes of low solids removal would be short circuiting in your clarifiers. You need to make sure that you're using all of your clarifier volume to slow down the flow coming into it, into the clarifier. If not, you might get short circuiting so you won't get as much solids settling. And remember, if your sludge bed's greater than 3 feet, you'll probably have some solids coming over the weir. So make sure your sludge depth in the bottom of your clarifier stays 3 feet or less. If you age the sludge too long by not pumping it, clarifier may become anaerobic. It will produce hydrogen sulfide and other gases that will cause the sludge to float, and it can float over your weirs and go into your secondary treatment system. A little math time. We're going to calculate pump rates. The units of the pump rate are gallons per minute. You divide the gallons pumped by the number of minutes the pump runs. Usually we'll be converting a volume into gallons to solve the problem. This type of math is not on your formula sheet. So a pump rate problem, 2 45-foot by 30-foot drying beds are filled with 1 foot of sludge from a digester in 2 hours and 10 minutes. What is the gallon per minute pump rate? We're going to work this one together. First thing you have to do is calculate the volume that you're filling the beds with. So we have 2 45 by 60 foot or by 30-foot drying beds with 1 foot of sludge in them. So it's 2 times 45 times 30 times 1 is 2,700 cubic feet. Remember, when you're doing this on test day, you have to put the number of beds you have. That's the second biggest mistake made on wastewater math, failure to include both beds in this case. Times 2,700 cubic feet times 7.48 gallons per cubic foot gives you 20,196 gallons. Failing to multiply by 7.48 is probably the mistake made most often on the wastewater test. So include the number of drying beds, the number of clarifiers, whatever we give you, and remember, if you want the volume in gallons, to multiply the cubic feet by 7.48. Next, we calculate the time. You get 2 hours and 10 minutes, 60 minutes in an hour. 2 times 60 is 120, plus 10 means it took 130 minutes to pump that 20,196 gallons onto those drying beds. So then you take the gallons of the volume of sludge in gallons divided by the minutes the pump ran. So 20,196 gallons divided by 130 minutes means the pump rate was 155.35 gallons per minute. So it's volume of sludge in gallons divided by the minutes it took to pump the volume that you're putting on the beds. Okay, here's one that you can try now. 3 50 by 30 by 50 foot drying beds were filled with 15 inches of sludge from a digester in 3 hours and 45 minutes. What is the pump rate in gallons per minute? Remember, if you get a measurement in inches, you have to convert it to feet before you start. So go ahead and try this, pick your answer, and I'll be back in just a minute. Okay, what answer did you get? The correct answer is 187 gallons per minute. Now let's see how we got that answer. First, we have to convert the 15 inches into feet. 15 inches divided by 12 inches equal 1.25 feet. Then we calculate the volume of the beds. There were 3 beds that are 30 feet by 50 feet, and you put 1.25 feet of sludge on each bed. So the volume is 3 times 30 times 50 times 125, which gives you 5,625 cubic feet. We need that in gallons. So we multiply it by 7.48, and that gives us 42,075 gallons. So we have the volume in gallons. Now, how long did it take to pump? It took 3 hours and 45 minutes. 3 times 60 is 180 plus 45 means it took you 225 minutes to pump that 42,075 gallons. So you take 42,075 gallons divided by 225 minutes, and it gives you a pump rate of 187 gallons per minute. Remember, when you're reading your book, to work all the math problems that are in the book. Work them more than once so you get familiar with how to work the problems. You may also go to our website under test preparation material and download the wastewater math study guide and work the problems on that too. The study guide is divided into 2 parts. The first part is the math that the class 1s and 2s need to concentrate on, and the other is for the class 3s and 4s. Sorry, 3s and 4s, you need to know it all. Class 1, 2, 3, and 4. Okay, here's a pounds formula math. How many pounds of sludge will be loaded onto 2 drying beds 30 feet wide and by 70 feet long to a depth of 12 inches with a concentration of the sludge of 23,400 milligrams per liter? Go ahead and try to work that one out. When it says pounds, what's that mean you're going to use? You're going to be using the pounds formula. Okay, how many pounds did you figure you put on the beds? The correct answer is 6,128 pounds. Let's see how we do it. There's your question again. How many pounds of sludge are loaded onto 2 drying beds, 30 feet wide by 70 feet long, to a depth of 12 inches with a concentration of 23,400 milligrams per liter? Convert the inches into feet. 12 divided by 12 is 1 foot. Calculate the volume of sludge. 2 beds times 30 feet times 70 feet times 1 foot is 4,200 cubic feet. We need it in gallons. Times 7.48 gives you 31,416 gallons. For the pounds formula, you need that converted to million gallons. So take your 31,416 gallons divided by a million, gives you 0.0314 million gallons. Now you calculate the pounds using the pounds formula. So it's million gallons times 8.34 times milligrams per liter. So our million gallons is 0.0314 times 8.34 times our concentration of 23,400 milligrams per liter. Do the math, and you get 6,127.9 pounds. Detention time. It's a design criteria for the primary treatment process. It's the time required to fill a tank at a given flow, or the theoretical time required for a given flow of wastewater to pass through a tank. Many of the treatment processes require a certain amount of time to effectively treat water. This is why knowing detention times is important. When you're designing a plant, you must be sure your tanks are large enough to give you the detention time you need at each step of treatment. Detention time math. Detention time is in hours. You take your detention time and multiply it by 24 hours in a day. What the equation is, it's the volume of your tank in gallons divided by the flow in gallons per day. So that would give you your answer in days. If you want your answer in hours, you then multiply it by 24 hours to give your detention time in hours. Volume of the tank in gallons divided by flow in gallons per day. If you need it in hours, then you multiply it by 24 hours. The flow to a 75-foot diameter clarifier with a 10-foot water depth is 2 million gallons per day. What is the detention time in hours? So again, we'll work this one together. You have to get the volume of your tank. Since we said it's a 75-foot diameter clarifier, you know it's a round tank. To get the volume of a round tank, it is 0.785 times diameter in feet times diameter in feet times depth of the water. So in this case, it's 0.785 times 75 times 75 times 10. That will give you your tank volume in cubic feet. You need it in gallons, so you must multiply by 7.48, which makes the volume that tank will hold is 330,288.7 gallons. Your flow in gallons per day, We said it's 2 million gallons a day. 2 million gallons a day equals 2 million. You must put it in with all the zeros. So you take your 330,288.7 gallons divided by 2 million. Since you want it in hours, that's what it asks you for, times 24 gives you 3.96 hours. It takes 3.96 hours for the first drop of water, when it enters the tank to that same drop of water goes out of the tank. Okay, here's one for you to work. What is the detention time in hours for an extended aeration treatment plant with 3 aeration basins, 50 feet by 40 feet by 12 feet deep, with a daily flow of 1.3 million gallons per day? Go ahead and work that out. We'll go through how to do it in just a little bit. Okay. What was the detention time? How many hours did it take that 1.3 million gallons per day to flow through those 3 aeration basins? Correct answer is 9.84 hours. Let's see how we do it. You got to find the tank volume in gallons. It's length times width times depth times the number of tanks. So it's 50 times 40 times 12 feet deep times 3 is 72,000 cubic feet times 7.48 to get gallons, and that gives you 538,560 gallons. Your flow, we want to divide that by the flow in gallons per day, 1.3 million. Take 1.3 times a million, it gives you 1,300,000 gallons. So it's 538,560 gallons divided by 1,300,000 gallons, which gives you 0.41 days times 24 hours in a day, gives you 9.84 hours. There are more examples of this in the book and on the math study guide. Okay, weirs. Weirs are installed along the edge of the effluent launder channel to skim water evenly off the surface of the clarifier. Weirs must be level to pull water equally from the entire tank surface. If your weirs are not level on your tank, you're going to be pulling more water from one part of the tank than you will the other. And that can cause scouring on the bottom of the tank at that location, which will cause you to pull solids over the weir and into your secondary treatment. The most common type of weir used is the V-notch weir. It's a plate that has notches about 2 to 3 inches deep, cut in every 6 to 8 inches. When excessively high velocities occur going over the weir, the settling solids are scoured from the bottom of the tank and are pulled over the weirs and into the effluent troughs. The weir overflow rate is another design criteria for clarifiers. The number of gallons of water that is discharged over the weir is based on the length of the weir in feet and the gallons per day flow going into the tank. The calculation of weir overflow rate is important in detecting high velocities near the weir, which can adversely affect the efficiency of the sedimentation process. Primary clarifiers should be designed so that the weir overflow rate should be between 5,000 and 15,000 gallons per day per foot of weir. Here's a weir overflow rate math problem. We'll work this one together. The flow rate to a 100-foot clarifier is 2.1 million gallons per day. What is the weir overflow rate? Since we only gave you one number, that it's a 100-foot clarifier, that means the tank is round and that's the diameter. The weir, remember, goes all the way around the edge of that tank. So you must calculate the circumference of the tank. To calculate circumference of the tank, you take the diameter of the tank times pi, which is 3.14. Calculate the length of weir. Since we have the diameter, we need to calculate the circumference. Circumference equal pi times diameter in feet. 3.14 times 100 feet means the weir is 314 feet long. We take our flow to the tank in gallons per day. 2.1 million gallons is 2,100,000 gallons per day, divided by the length of weir, 314 feet, gives you a weir overflow rate of 6,687.9 gallons per day per foot of weir. Here's one for you to work. The flow to a 120-foot clarifier is 2.8 million gallons per day. What is the weir overflow rate? Go ahead and try it. And then we'll work it together. Okay, what did you get? What's the weir overflow rate? How many gallons per day per foot of weir? Correct answer is C, 7,431 gallons per day. Again, you have to calculate the circumference to get the length of weir. Since it was a round tank, we only gave you one number, which means the tank is round. So it's pi times diameter. The diameter was 120 feet. 3.14 times 120 feet means that your weir was 376.8 feet long. Your flow was 2.8 million gallons a day, which is 2,800,000 gallons per day, divided by your length of weir, 376.8 feet, gives you a weir overflow rate of 7,431 gallons per day per feet of weir. 7,431 gallons per day per feet of weir. Surface overflow rate is also used to size primary clarifiers. You've covered it in chapter 3 in the biology section. It's hydraulic rate. It's the gallons per day per feet of surface area. So it's gallons per day per square foot. If you have a round clarifier, the number of square feet is 0.785 times the diameter in feet times the diameter in feet. That would be the square footage. If it is a rectangular tank, it would be length times width would be your surface area. Divided, you take flow in gallons per day divided by the square feet. That finishes up the primary clarifier part. Now we will go to fixed film or attached growth rate reactors. This is a form of secondary treatment. The bacteria in these reactors are attached to a surface or a media, either rock, plastic, wood. The wastewater is then passed over the media. Oxygen is added to the water by blowing up through the media, allowing the bacteria to grow, and these bacteria will eat the BOD out of the wastewater. The first thing we're going to talk about is a trickling filter. Basically, a trickling filter is a tank that's filled with either plastic media or rock. Water is spread over the top of the trickling filter using a rotating arms that spread the water evenly over the surface of the rock. As the water runs through the media, the bacteria attached to that media will use the BOD for food to reproduce. Here's their cutaway view of a trickling filter. The top, you have your rotating distributor that evenly distributes water over the top of the media. Your influent, it gets to the arm, it goes up through a pipe and comes out through the distribution arm. The water will flow down through the media. At the same time, your underdrains are allowing air to come up through the media. So the bacteria have air, the oxygen they need to use the BOD as food. As the water comes off of the media, it goes through the underdrain and onto your effluent. Also, any biofilm that builds up on the media, when it gets too heavy, it will fall off, and it also goes out with the effluent into your secondary clarifier. An entire trickling filter system is shown with this picture. The primary effluent comes in. It's mixed with the recirculation water from the primary clarifier, goes up to the distribution arm, down through the media, into the clarifier where the solids fall out. The clarified water, part of it goes on to disinfection, part of it's used as recirculation. Why do you have recirculation in a trickling filter? Recirculation is used during low flow to dilute the influent organic strength. You want to try to keep a fairly constant level of food going to a trickling filter. You can use the recirculation to equalize flow variations. It increases contact time with and seeds the filter media. Your water will flow over that media more than one time. And it keeps the distributor arm in motion to prevent the drying out of the media. A lot of the trickling filters do not use power to power that distributor arm. The force of the water coming out will turn the arm. For trickling filter math, we calculate organic load. Here's a formula. We'll work, or a question. We'll work this one out together. The primary effluent flow is 1.2 million gallons per day with a BOD5 of 123 milligrams per liter. Flow enters a 100-foot diameter trickling filter that is 5 feet deep. Each cubic foot of volume contains 30 square feet of filter material. What is the organic loading in pounds of BOD per cubic foot? So it's pounds of BOD over the volume in 1,000 cubic foot units. If they're asking for BOD per 1,000 cubic feet, you can ignore the line that says each cubic foot of volume contains 30 square feet of filter material. The only times that's used, we'll see here in a little bit. So we want pounds of BOD over the 1,000 cubic foot units. So there's our equation again. The first thing we need to do is calculate the BOD. It's 1.2 million gallons times 123 milligrams per liter times 8.34 means you have 1,230.98 pounds of BOD per day going over that trickling filter. To get the volume in 1,000 cubic foot units, you calculate the volume of your filter. It was 100 feet in diameter, 5 feet deep. So we take 0.785 times 100 feet in diameter times 100 feet in diameter times 5 feet deep. We get 39,250 cubic feet. Since we want 1,000 cubic foot units, we divide that by 1,000, and the volume is 39.25 1,000 cubic foot units. We have the BOD, we have our volume, then we calculate the organic loading. It's pounds of BOD, 1,230.99 divided by 39.25 1,000 cubic foot units, which would give us 31.36 pounds per 1,000 cubic foot unit. Class 3 and 4, when you see questions like this on your test, read it carefully. If they ask for pounds per 1,000 cubic feet, you do it just like we did. If they ask for pounds per square foot, you cannot ignore the line that says each cubic feet of volume contains so many square feet of material. In this case, it's the exact same problem, except what is the organic loading in pounds of BOD per 1,000 square feet? Read all the problems carefully, including the word problems. Read just the ones that aren't math. Read them carefully to make sure you know what they're asking. We'll work through this one for the 3s and 4s. So your organic loading in pounds per 1,000 square foot unit is pounds of BOD 5 over the volume in 1,000 square feet. Calculate the pounds the same way we did before. 1.2 times 123 milligrams per liter times 8.34 gives you your 1,230.98 pounds. Calculate the volume the same way. 0.785 times 100 times 100 times 5 gives you 39,250 cubic feet. Now we have to calculate the media because they want it in 1,000 square foot units. So take your volume, 39,250 cubic feet times the 30 square feet of media per cubic foot in the tank. That will give you 1,177,500 square feet. You divide it by 1,000 because we want 1,000 cubic foot units. So that gives you 1,177.5 1,000 square foot units. Take your BOD, 1,230.99 divided by 1,177.5 1,000 square foot units. And your organic loading for this filter would be 1.05 pounds per 1,000 square feet of media. So 3s and 4s, read the question carefully. Trickling filter operation. Organisms are attached to the media by a slime layer or biofilm that absorb the organic material in the wastewater. As the biofilm thickens, microorganisms fall off the media. These are called slough solids. Periodically, too, what you'll see a lot of people do with trickling filters, they'll slow down the speed of the distribution arm if it's not one that's just pushed by water. If it's controlled by a motor, they can slow it down once or twice a day to help wash the microorganisms off the media so they don't get too heavy. The underdrain system is important, so free passage of air is available. This also collects the effluent and the slough solids to transfer to the secondary clarifier. Next, we will look at rotating biological contactors, or RBCs. This shows you the media out of the tank so you can see what it looks like. This would be one stage of media. Here's a picture showing you an RBC system. You'll notice you have 4 trains, 4 units wide. Each unit wide's a train. Each train has, in this case, 1, 2, 3, 4, 5, 6 stages. So this one is 4 trains and 6 stages. This shows you a broken out picture of an RBC. This is one train they're showing you. This train has 2 stages with media in each stage. These wheels are constantly turning. About 40% of the media is submerged at one time. The shafts are generally 25 to 27 feet in length. The media diameter is about 12 feet. Like I said, about 40% of the media is submerged. These stages are turning. And what that turning does is it allows air to mix into the wastewater. You need 2 to 3 stages to achieve BOD limits. 3 to 4 stages are needed to achieve a BOD effluent of less than 20 milligrams per liter. If you're looking for nitrification, you'll probably have to add additional stages, typically at the end with higher BOD levels at that point, or higher oxygen DO levels at that point. Standard density media for BOD removal is about 100,000 square feet per shaft. Loading for the first stage is 2.5 pounds of soluble BOD per 1,000 square feet. High density media is usually used for ammonia removal, and it is 150,000 square feet per shaft. If there is a question on your test, a math question, and it does not say high density, then you assume the media is 100,000 square feet per shaft. A healthy first stage biomass on your RBC media is uniformly brown and distributed in a thin, even layer. If you look at this picture, you'll see the media looks like it's got white or grayish filamentous growth on the filter media. That's typically a result of low DO and or high hydrogen sulfide concentrations. So if you see that forming, you do not have enough DO in your water, or you've got high concentrations of hydrogen sulfide where your water is going septic. Dissolved oxygen levels in RBC, typically at the end of the first stage, the DO will be 0.5 to 1.0 milligrams per liter. At the end of the last stage, it's typically 2 to 3 milligrams per liter. Unless the RBC is designed for nitrification, then it should be 4 to 5 milligrams per liter minimum. RBC math, calculate the pounds of soluble BOD5 per day per 1,000 square feet on the first stage media of a rotating biological contactor plant. The plant is using all 4 trains. The design is 2.2 million gallons per day, contains 4 trains and 5 stages. Each RBC unit on the first 3 stages contains 100,000 square feet of media. Each RBC unit on the 4th and 5th stages contains 150,000 square feet of media. Flow is 1.9 million gallons per day. Influent BOD5 equal 250 parts per million. The soluble BOD is 60% of the total BOD. Calculate pounds of BOD using the pounds formula. Account for the soluble being 60% of the total pounds. Remember, we just want to know when we're talking about RBC loading, all we're worried about is the first stage media. So this one has 4 trains. Each one has 100,000 square feet. What would that give you in square footage for the first stage of the media? 4 times 100,000 or 400,000 square feet. So first, let's calculate the pounds of soluble BOD. We're going to use the pounds formula. It's pounds of BOD equal 0.9 million gallons per day times 8.34. Now your influent was at 200 milligrams per liter, but only 60% of that is soluble. So you take 60% divided by 100, it gives you 0.6. So 200 times 0.6 would be the soluble BOD. You do the math and you get 900.7 pounds of soluble BOD. You calculate the area of the filter used in 1,000 cubic foot units. You have 100,000 feet per train. There are 4 trains. So you have 400,000 square feet. You divide that by 1,000 to convert it to 1,000 square foot units. And you end up with 400. 400,000 divided by 1,000 is 400. 1,000 square foot units. Take your BOD, which is 907 pounds, divided by the surface area of the media in 1,000 square foot units. It's 400. 1,000 square foot units gives you a loading of 2.25 pounds of soluble BOD per 1,000 square feet. That's less than 2.5 pounds per 1,000 square feet, so your unit is not overloaded. Combined processes. They can combine the advantages of attached growth and suspended growth systems. They provide stability and resistance to shock loads of attached growth processes. They'll provide high quality effluent or increased nitrification of suspended growth systems. So you can have the activated biofilter. Sludge from the secondary clarifier is mixed with the influent and fed directly on the filter. The low BOD loading is required for reliable treatment, typically less than 100 pounds of BOD per 1,000 cubic feet per day. So remember, you're only taking the sludge from the secondary clarifier and mixing it with some of your influent to feed onto the filter. And this is not well suited for colder climates unless it's aerated. You can have trickling filter solids contact. It's used for moderate to high BOD loads. A small aerated contact unit is added after the trickling filter. It allows you to downsize the size of the trickling filter you would normally need. 60 to 85% of the BOD is removed in the trickling filter. You can have a roughing filter activated sludge system. It's used to upgrade existing activated sludge plants by installing a smaller roughing filter ahead of the aeration system. It's similar to the trickling filter solid contacts process. It operates at higher total organic loadings with a smaller filter. It depends more on the aeration basin to provide oxygen and remove BOD and to digest the solids. The biofilter activated sludge. All return activated sludge from the clarifier is recycled over the trickling filter in similar fashion to that of other activated biofilter processes. It'll help you treat higher BOD waste, and it's typically used to provide an impact for food processing waste, that are typically higher BODs. And you could have series trickling filter activated sludge. You have an intermediate clarifier is located between the trickling filter and the aeration basin. The slough solids are removed by the clarifier from the trickling filter underflow before entering the aeration basin. When the removal of nitrogen is a priority, the BOD removal is achieved on the filter before the activated sludge process. Remember, for nitrification, you need to operate at higher BODs in the activated sludge part of this plant. And that ends chapter 5, part 1. If you have any questions on this chapter, you may send an email to envhelp@ky.gov or call 502-782-6189 with your question. Your question will be forwarded to a trainer who will get in touch with you